I want to come back to the question of equivalence of algebraic probability spaces, because last time I discussed only the notion of stochastic equivalence, and I want to mainly show you the subtle relationships between different notions of equivalence, which are all considered in classical probability and also in von Neumann algebra. So remember, the notion of algebraic probability space is a pair. Somebody called quantum, but quantum is not a good name because it doesn't distinguish, it doesn't include the classical case. I use the term algebraic probability space because when the algebra A is commutative, we call classical. When the algebra A is non-commutative, we call quantum. We want to have a generalization of classical probability theory, not a... Okay, the cyclic representation we already discussed last time. And so what I want to discuss today is what are the natural morphisms in the category of algebraic probability spaces. So the precise definition is slightly more general than the one I gave last time. First of all, we introduced the notion of absolute continuity of two algebraic probabilities. In algebraic, we want to translate the measure theoretical absolute continuity into the algebraic absolute continuity. So when do we say that two probability, algebraic probability, one algebraic probability, we have two algebraic probability spaces, A1 phi1 and A2 phi2. We say that A2 phi2 is absolutely continuous with I wrote the converse here is in fact not very, sorry. This you have to interchange the two indices, A2 and the A1 for the definition that I used below. I will give you an example. So we say that the algebraic probability space A2 phi2 is absolutely continuous with respect to A1 phi1, and we write this with inverted index, please, if if there exists an isometry of the corresponding cyclic spaces, pay attention, the isometry goes from H2 to H1, such that if I denote this homomorphism, star homomorphism, implemented by the isometry, remember isometry means that U star U equal the identity. This is the definition of isometry. Then you see, since U goes from H2 to H1, U star will go from H1 to H2. So I can apply an operator in H2 on the inverse image of such a U star image of a vector in S1, and then bring back to H1. So I obtain an homomorphism. The homomorphism is due to the isometric property that I wrote there, homomorphic property. And what we require is that when I restrict this homomorphism, star homomorphism, which is defined on all B of H, to the bicommutant of P2A2, I obtain a von Neumann W star von Neumann algebra injective homomorphism. Okay? Also here there is another misprint remained from the other lecture. The homomorphism in this case is not surjective, it is injective. I will show you in a moment an example to be more clear, to make it more concrete, this abstract notion. Now we pass to the stochastic homomorphism and corresponding stochastic isomorphism. We speak of a stochastic homomorphism when we have the condition of absolute continuity plus the condition of intertwining of the states. This will correspond to the preservation of measures. Finally, we introduce very strong notion of isomorphism that is much less used in probability theory, but is very much used in operator algebra theory, which is defined by the fact that the two states are intertwined. So I take U will map an element of, again, this indices must be intertwined. U will map an element of A2 into A1. So here I should apply P1 and Phi1, and here I have Phi2 and P2. Maybe it is much better to give a concrete example. So let me, as a concrete example, take as A1 the finitely valued step functions, okay? From the interval 0, 1 to the complex number. And as A2, the bounded continuous functions from 0, 1 to the complex numbers. And I take, in both cases, the same in quotation marks, but it is the state is implemented by the same measure, and the measure is just Lebesgue measure on 0, 1. So it's a very particular case. In this case, the spaces, the cyclic spaces are the same. Because both by completing the step functions and the continuous bounded function, I will obtain, with respect to the same measure, Lebesgue, I will obtain L2 of 0, 1. Of course, the two algebras are not isomorphic, so there is no strong isomorphism of algebraic probability spaces. However, in this case, we have stochastic equivalence because the measure is the same. The space is the same and the cyclic vector is the same. So we have stochastic equivalence. Moreover, the isomorphism is U that was defined in the abstract definition is simply the identity function. Because the von Neumann algebra in both cases is L infinity with respect to Lebesgue measure. To give an example of absolute continuity, which is not a stochastic equivalence, a stochastic isomorphism, let us consider the same measure, a measurable space, and on this measurable space, that is a space omega with a sigma algebra F, on this measurable space, we take two probability measures, and we suppose that P2 is absolutely continuous with respect to P1. This means that it has the same zero sets. Not the same. The zero sets of P2 are contained in the zero sets of P1. the algebra we choose, before we choose two different algebras and the same measures. Now we choose the same algebra, but two different measures on it. We take the algebra to be L infinity, the bounded measurable functions for the sigma algebra F from omega to the complex numbers. The algebra is the same. The states are different because the state is the integral with respect to the measure Pj, and j goes from 1 to 2. In this case, what are the cyclic spaces? The cyclic space Hj will be the L2 of the measurable space, which is the same, but with respect to the measure Pj. What is the cyclic representation Pj? Pj will associate to every function f the Pj class of f. F is a function in L infinity, so it's a measurable function, and the Pjf is the Pj class of f with respect to this equivalence relation. This equivalence relation means that they coincide, the two functions f and g coincide Pj almost everywhere. With this definition, the cyclic vector Pj will be the Pj class of the constant function equal to 1. Of course, this map, take a function f in L2 with respect to the measure, sorry, again, index wrong. This is index should be P2. In the L2 space of P2, and associate, no, sorry, this is correct. Just a moment.
That would be H.
It's correct. F, yes, this is correct. Because if I integrate with respect to the measure P2, I get an isometry.
H2 and H1.
Huh?
H2, H1 should
Yeah. This goes in the correct direction. Okay? Well, in fact. However, this isometry will map the identity function of P1 into this vector, which is square integrable for P2, but is not P1. Phi 1. And the isomorphism that we described before simply considers is an isomorphism that has a very strong property that here it has a meaning because the star algebra is the same. This isomorphism intertwines the two representations. So this means that I take a class of function with respect to the P2 measure is mapped into a class of function with respect to the P1 measure. And it is well defined because the zero set of P2 are contained in the zero set of P1. So we have something stronger than pure absolute continuity, because the algebra is the same, and this property is meaningful. When the algebras are different, this property would have no meaning. So, the notion of algebraic absolute continuity of probability space, in this example, reduces to the usual absolute continuity, and therefore the notion of equivalence of algebraic probability space becomes, the algebraic equivalence becomes simply that the two measures are equivalent in the measure theoretical sense. And then, of course, we can always, using cyclic representation, suppose that our algebraic probability space is concretely represented as an algebra or densely defined operator on the Hilbert space. So it's important to remember when you think to some special applications, for example, orthogonal polynomial, that at a pre-Hilbert space, the operators are everywhere defined. At Hilbert space, they are densely defined. Okay, yesterday I wanted to in the previous lecture, I claimed that I want to show you a very general lemma, which is at the basis of the central limit theorem. It contains the essential point of central limit theorem. And I emphasized that this essential point is purely combinatorial. It has not to do with probability theory in some sense, because we don't need positivity, we don't need the existence of an identity. We don't need the star algebra structure. We need algebra structure because we need multiplication. So the context, I recall you the context. I have a family with two indices. I have a single algebra and a family of sequences indexed by a set S. S in typically, for the moment, think a finite set D, and typically, for example, if you have in mind orthogonal applications to orthogonal polynomial, our set D in the following will be simply the set of first small d natural integers, okay? So you should imagine, you should think of this index S as an index of the components of a random variable. There is a quantum operator variable that is because we discussed. So let me just fix this notation so you will remember. Here Bn is Bns is an element of A. N belongs to a general set that can be a graph, or for the moment we don't use any structure, just a set, a countable set. And S belongs to this finite set D. For future notation, En is a sequence of states, parameterized, so is a knot of states of linear maps from A to a certain normed space. We don't require C to be an algebra. In the concrete application to standard central limit theorem, C will be the complex numbers, okay? So this is a normed space. And the family of maps is indexed by finite subsets of V. In fact, we will restrict it to a certain family F. And the basic example you should have in mind is when V, this corresponds to the standard central limit theorem in probability theory. The set V is the natural integers, and the family F is the family of all intervals 0n, ordered by standard inclusion. Also here, this family F is supposing to be what is called a net or a filtering increasing system. Family. So this will be our framework. And yesterday we discussed, not yesterday, last previous lecture, what will be our main concern. I will write our main concern in the following will be the study of this of the asymptotics as n goes to infinity. You remember the definition of n converging to infinity in a net. So we will study this kind of sums. And the sums be, this is the normalized sum over this will denote cardinality. The cardinality of the set n to the power alpha, and then I sum over all n in this set n, and I will sum over the index n. So when we consider only this sum without a normalization, we write simply as n. So this will be equal by definition to the cardinality to the power alpha of Sn of Bs. I write this notation on the blackboard so you in the following will remember. Okay. Now we said the last time, the previous lecture, that when alpha is equal 1, we have the law of large numbers. And when alpha is equal 1/2, and in addition, we have that the Bn has 0 expectation, this corresponds to the central limit theorem. We will, today, I want to jump the discussion of fluctuation and etc. was discussed in previous lectures. I will jump them, and we will arrive to what is the core of the present talk. We also discussed, I showed why the index alpha equal to 1/2 is very special. So essentially, for this formulation, this is called, as I want to emphasize, it's called the moment central limit theorem. For us, central limit theorem will be equivalent to moment central limit theorem. I will not repeat. So the convergence will be a very special convergence of mixed moments in the non-commutative sense. I recall the singleton condition. The singleton condition that we introduced last time is the following one. I give in general. Suppose that well, here the definition is given in general, and you can suppose to match the general definition with the special condition that we had here for central limit theorem. The code of translation will be the following. If you take alpha belonging to V, then the A alpha will be, by definition, the linear space, the linear span, is a subspace, not necessarily an algebra, of our this. Okay, so in what we are interested, we will have a map. We will consider what are the mixed moments that we are interested in. We are interested in the mixed moment of this form. For each n, when I write n, it is understood that it is in this net. For each n, we will have this product, and we fix a number k. We have S1 of n over n to the power alpha of B S1. And this is a product. I will consider a product of k non-commutative factors. S is not index. Okay, so this will be our general framework. Remember, S will be a function from k is now a natural integer, and S is a function with values in the set D. So many values of S can be repeated. If the algebra is commutative, we can commute and have S to some power. But these are called the mixed moments in the non-commutative case. Okay? So what is the singleton condition? I explained, I discussed in more detail last time. And the singleton condition means this. If there is a single j such that A sigma j is mean 0, and this index sigma j is never repeated in the set sigma 1 sigma k, then this expectation is 0. In the previous lecture, we have proved that this singleton condition, when the algebra first is commutative, second contains an identity, then it is perfectly equivalent to standard classical independence. Okay? So this is the fundamental, and you will see in a moment why this condition plays a basic role.
This was first
Not positive.
probability or
No. This is purely combined. This En, I want to insist on this point because it's very important, are arbitrary maps into a normed space. Arbitrary. For example, I made the example last lecture, that En, for example, instead of being a measure, can be a conditional expectation. Or it can be a completely positive map. Or it can be a map without any positivity condition.
So you see, it is an algebraic structure that is enforced with this condition essentially. You don't need positivity, you don't need to be.
No. for the basic lemma I'm going to prove today. This basic lemma will show you up some, in some sense.
Linearity is there.
Huh?
In each component, it's a multilinear functional in some sense, right?
Yes, because there is the product. This is standard. I need algebra structure because otherwise I cannot speak of mixed moments. In order to speak of mixed moments, you need an algebra structure.
The map is actually multilinear in that sense.
This map is multilinear, and in fact, it is a very special multilinearity because it has probably, what you say is right, probably it could even be generalized. I may also drop the condition that the multilinearity factorizes as a product in an algebra and a certain linear map. But this is a small generalization because it's well known that if I have a multilinear map, I have a linear map on the tensor product. Okay? So I can always reduce to this. To go from such kind of structure to general multilinear En is not a very big generalization. Can always be reduced to this case, going to the tensor algebra. Now we put a second condition. So we have a first condition, which is algebraic, and in fact of a statistical nature, because this is the singleton condition is a very special condition on the map En. So it is a statistical assumption. Now we do an analytical assumption, which is boundedness of the moments. This boundedness of the moment is important in the following. It is a kind of extremely weak stationarity condition. So these moments have a bound. Pay attention that the bound depends only, that is why we call uniform bounded, is uniform with respect to the index sigma. So independently of the index sigma, this expectation value has this bound. Let me give you some example to show that this bound is extremely easy to satisfy. So suppose now that I take A to be a C-star algebra. For example, an algebra of matrices. Historically, the first central limit theorem were done on algebras of matrices. Of course, they are C-star algebra. So if it is a C-star algebra, what this condition is is implied that because all elements of a C-star algebra are bounded. So what is this condition? If I have a C-star algebra and En is a state in the usual sense, then of course, in fact, even if it is not a state, it is any linear functional. But I want linear functional to be continuous in the norm topology of the C-star algebra. In that case, C will be the norm of the expectation value, the linear functional En, and of course I have this bound. So you see that this condition of uniform boundedness of moments means in a C-star algebra framework that I have the uniform bound in N of the norms of these elements. Now, suppose that we have the following weak algebraic stationarity condition. You see, in my abstract setting, the Bn are arbitrary, but what are the concrete examples? In the concrete examples, you have a C-star algebra B with identity. Typically, B is an algebra of matrices. And you have a star homomorphism such that the AN, this, in fact, I say here that A alpha is a linear span, but when you are a sister algebra, you can take algebraic span, so you can take the algebra. And you have this AN are all isomorphic images of the same sister algebra B. I will give you a concrete example from classical probability in a moment. In this case, it is well known that in sister algebra, homomorphisms have norm 1. Therefore, the boundedness condition is automatically satisfied. Okay? So the uniform boundedness of the moment in stand is not a very heavy requirement. Let me give you one important example, because this is crucial to understand. This will be crucial to understand our notion of algebraic stochastic process. So take a classical stochastic process, a sequence by discrete index. So we have a classical probability space, and we have a real valued stochastic process. And n is the natural integers. Then, for every bounded measurable function f from R to C, I can form the composite function, which to omega in omega associates f of xn of omega. Okay, this is this function. Now let me consider, so this is by definition the composition of f with the random variable n, evaluated in omega. Okay? Thank you. Good. So, if you consider this map as a map in the variable f, you obtain the basic example of our homomorphism. The algebra B abstract here is simply L infinity of R, with usual, without Lebesgue measure, not the classes of function, just the Borel measurable functions. And I associate to any measurable Borel function the random variable f composed with xn. It's obvious that this is a star homomorphism. Okay? This will be our fundamental example. Of course, such an homomorphism completely characterizes the distribution of the random variables, even the joint distribution, and therefore it completely characterizes the process. What are the mixed moments of such a process? The mixed moment will be P of F1. P means the integral with respect to P. I use the same letter algebraically. F1 X to put the same. You see, here in our case, N is our index V. Okay? So the mixed moments will be of this form. Okay. This mixed moment of order K will be of this form. for all possible choices of n1 and k inside the index set. Okay? This, this will this example is an example in which this condition of uniform boundedness of the, that's all. I don't need any stationarity if I have the C-star algebra property, okay? This condition or uniform boundedness of the processes, you see, since it is multilinear in the B, it will continue to take place if I replace each B by a linear combination. The only requirement is that all linear combinations have the same number of, or have a number of terms which is bounded by a given fixed natural integer. I want to do another example to be more, so this is example 1. This is example from classical probability. Another example from quantum probability is very important when we do concrete central limit theorem is the following. Take MD, the matrix algebra, the D by D complex matrices, okay? And let, in our case, in this case, the algebra A is simply the algebra of the this probability space, the bounded functions on the probability space. This is in our case. In this example, the algebra A will be the infinite tensor product of MD. And the homomorphism Jn will simply be the map Jn, which to an arbitrary matrix in D by D matrix will associate the matrix itself as an element of this tensor product. So I take the identity on the set theoretical complement of C in the real numbers n. Okay? So this is by definition n minus the index n. Okay? This means simply that I embed the matrix algebra in this product in the obvious way by taking A in the nth factor and the identity everywhere else. Okay? So this is the Jn. Of course, this condition is satisfied by the general argument that we said. So we have a lot of examples in which this condition of uniform boundedness on moments comes very cheaply, I mean, without any cost, simply from the statement of the problem. Okay. These are the only two assumptions I will need. So I will write the second assumption. So these are the objects we study. I erase the examples because I hope you will have understood them clearly. And I will list the two assumptions that I will need in the following. So, first assumptions. One is the En, the family En satisfies the singleton condition. Second, uniform boundedness of the moments. So, since C is a normed space, here I use the norm of C just to formulate the uniform boundedness condition. And if I have a product of this B, this will be bounded by a number M depending only on the index S1, Sk. Remember, the index is the index of the component of the vector valued random variable, not on the algebra to which this operator, or space to which this operator belongs. These are my only assumptions. Now, I want to show you what is the what I anticipate what will be the final result. The final result is that under these two assumptions, when we take this limit for n going to infinity in the net sense, the limit will be expressed of a product of pairs, not any other partition. You will have a partition of the set 1k, the index set, which is fixed. N will vary and go to infinity. And the limit of this.
What will be the value of the range of alpha then?
Please?
In your theorem, what will be the value for alpha? Well, alpha is any value between?
We will see. Very good question. I forgot. We will see in a moment. It is in the assumption. I will show you. Because we have seen when we did the necessary condition that if alpha is less than 1/2, strictly less, the limit of the covariance, that is of the 2 point of the second moment, is always 0. So if E is a state by the Schwarz, or just if E is a positive map, well, a little bit more, is a Schwarz map, which satisfies the Schwarz inequality. If E is a Schwarz map, the fact that the second moment is 0 implies that all moments are 0. So the case alpha less is already ruled out in the most interesting applications. Therefore, we will study this limit in the range alpha greater or equal than 1/2. And we will see that when alpha is strictly greater than 1/2, this limit is identically 0. So only the 1/2 possibility. Here the mean 0 condition will enter. Okay? Mean 0 will be fundamental. But mean 0 plus singleton plus uniform bound, I mean, these two assumptions are important. So the only possibility will be alpha 1/2. Okay? So why, what is, first of all, yeah, this is what you were asking. That we already proved, that I already explained this. So that we consider only this range of alpha. So let me formulate this fundamental lemma. So the two assumptions are those that I wrote here. 1 and 2. Oh my God, very, very, very short time. So I consider the mixed moments. Remember that by definition, this is the normalized sum, Sn alpha. So I have a common factor of n power alpha for each of these terms of the product. This justifies the appearance of this factor here. I have 1 n alpha, a modulus n, cardinality of n to power alpha for each factor. The factor are k, so this is the normalization. And Sn is the non-normalized sum, written there. And I claim that. Sorry, but this is. So, if alpha is strictly greater than 1/2, I have an explicit bound on this mixed moment, mixed moments that we are studying, namely this one. This mixed moment in norm, remember, the value is in the normed space, will be less or equal than this quantity. Now, S1 and K are fixed, and n goes to infinity. The cardinality of n goes to infinity. So this is what I said before. You will have 0 if alpha is strict. The constant C also can be explicitly estimated. P in this, I did not write, but P in this formula is the integer part of K over 2. Okay. Now we consider the most interesting case. If alpha is equal 1/2. If alpha is equal 1/2, then we have to distinguish the case in which the moment is odd and the case in which the moment is even. If it is odd, we have still convergence to 0, a little bit slower, because it will go like the cardinality of n to the square root, not like the cardinality of n like before, but still will go to 0. What does it mean in the probabilistic interpretation? That with this kind of central limit theorems, with the singlet on condition, in the limit we can only get symmetric probability symmetric state. A state is called symmetric, is the generalization of a symmetric probability measure. For a probability measure, symmetric means that for a probability measure on the real line, symmetric means that for every subset of the real line, mu of A is equal mu to the minus A. And for a state on an algebra, a linear function on an algebra, symmetrics means that you have a family B is a subset of this algebra, not a subalgebra, subset. We will say that phi is B-symmetric if all odd mixed moments of elements of B are 0. So this means phi of B S1 B Sk equals 0 whenever K is odd and B Sj is an element of B. So this will be the algebraic definition of a symmetric state. The odd moment, of course, when you speak of mixed moment, it's like in a random variable. Remember, in a random variable in probability theory, you always say that you identify a random, you speak of a random variable x. But if you go to a vector valued random variable, to speak of a random variable x1, xd means that you have fixed a set of coordinates. So the algebraic analog of fixing a set of coordinates is to fix a set of generators in the algebra. Okay? And then the central limit theorems have to do with the generators of the algebra. So the odd moments will vanish, and here is the fundamental result. This limit will be sum up to something which goes to 0, like 1 over the cardinality of n, will be equal to the following expression. And in the following lecture, we will discuss conditions under which the limit of this expression will exist. But pay attention, what is very important of this expression? What I said before. Let me write here these moments. Because when you take the expectation of these maps, I want to use the same notation. When you take this, remember that Sn is a sum. Okay? Like this. Therefore, what will be when I expand explicitly this expectation and I expand the sums? I will have a sum over all possible functions. You see, this sum is indexed with value is indexed by the set n, and I have k factors. So I will all possible functions. I will have all possible functions from with values in n, and each of them will be a contribution. So from 1k with values to n of, and then I have to expand. I have the expectation, n expectation of b s1 sigma 1 b sk sigma k. So this will be the limit I want to study. And the theorem says that the main result is that I don't need to consider all these functions.
This is the absolute expression within all the error term of O1 by n. That's what he was.
Huh?
This expression is exact right now. The one on the right hand side.
This one.
Yeah, this is an exact expression, right? And you have
There is this difference. There is this. Okay? So up to something that goes to 0, like 1 over the cardinality of n. This sum, which is over all functions, in fact, can be restricted to a very special type of functions. Namely, which functions? Look, so sigma is a function from 1k, the set 1k to n. So let me call the range of sigma by definition to be sigma 1, sigma k. These are the sigma j that appear here. But I pay attention. I want the range as a set. So I want to eliminate from the range the duplicate values. Because it can be that sigma 1 is equal to sigma 2. So when I consider as a set, a priori it will be smaller. So it will be sigma 1, let us say sigma m, with m less or equal than k. Okay? It's clear at this point. I consider the range as a set. And I consider in this set one value. For example, if sigma is a constant function, then m will be equal to 1. Because sigma is only one value. Okay? In general, I anticipate something that it will come later. If I have sigma in the range of sigma, I will have the following partition of the set 1k. Is clear, this is a very fundamental point. Is clear or not? Or you have some doubt? The example I did of a constant sigma, here are all possible functions. So included the constant. In this case, when sigma is constant, the range has only one value. Okay? So this is the first estimate. What does it mean? What does it mean? It means that we are not solving the problem. We are just reducing the problem from the establishing the general limit of this sum to the general limit of a much smaller sum. And tomorrow I will show you how a detailed analysis of this will naturally suggest the introduction of the most fundamental notions of stochastic independence, free independence, and it will come from inspection of this analysis of this expression. But a last point is interesting, that in some sense the Gaussian case, we have an estimate of the error. This term is less or equal, is the same estimate as the first part of the theorem. The constant is also the same. And moreover, we have this, which is called the Gaussian bound. Why Gaussian? Because we will see that this combinatorial factor is precisely the one that, pay attention, k is equal to n. We only need the 2n because 2n plus 1 will go to 0. So in the case, this is the this combinatorial factor is precisely the factor that comes out in the Gaussian case. I am really very sorry, but yeah, what?
So it's only 5 minutes. Okay.
Right. I am afraid I prefer to go a little bit slower, but to be followed rather than to go. Of course, it's very easy, especially using transparency, to go very fast. But my goal is to try to convey to you the real essence of this. Is a very, very fundamental result, not only for quantum probability, for classical probability also, because it really goes to the very deep combinatorial.
In the limit, you're still getting Gaussian.
No. No, many. You will see. Everything will depend on the additional assumption. You see, we will do a lot of example.
Yeah,
Because only with example you can understand. You see, tomorrow I will explain why the fundamental point will be.
free independence with this prescription?
Yes, you will get free independence. It will. So the logic will be the following: if the algebra is commutative, then it is Gaussian.
Yes.
No other possibility. Then it will depend very much on
Accommodation relation between the objects.
there will be two types of condition. We will call the algebraic conditions like commutations. The second are statistical conditions like free independence. Free independence, there is no commutation a priori.
But it has the same Gaussian nature, that is breaking up into two pieces.
But this you read from this.
So even the free
This will be universal. This will correspond to the infinitely many notions of Gaussianity.
So you have some Bogoliubov transformation in case of free independence, of course. Gaussian independence, you have Bogoliubov transformation.
Yes.
You have something like Gaussian
We have Bogoliubov transformation for every Gaussian. Every Gaussianity. For free, for monotone, for Q-deformed, for any type of. You will see, I hope.
So you have an underlying symmetry in all your calculations.
The symmetry is an additional assumption. We don't need for central limit here.
It is implicitly there.
The implicit you can introduce,
Yes,
but
it's already there.
It is, but what is essential? Wait until the next lecture, and we will discuss the various kind of conditions that you mentioned. Okay? Yes.
In this equation, 1 by n is much slower decay than 1 by k power half, right? Means 1 by n is going at 1 by n rate, but k by 2 can be going down much faster.
It can be 2.
Right, yes, 3. So
Yeah.
1 by n power 3 by 2 is going to 0 faster than 1 by n, right?
What is going to 0 faster than 1?
Means if the limit n tends to infinity.
When the cardinality of n go to infinity, this is an exact estimate.
Yes, no,
Oh, you're saying actually what is the behavior?
the error term is the second term, right?
No, error term is the first.
First term is going at 1 by n rate. But
1 over the cardinality of n.
Yes.
Yeah.
But second term is.
Second term we will see. Second term will go to a constant in the standard cases. But for convergence, this is the most that you can do using only these two very, very abstract and general assumptions. For convergence, you need something more. What more?
The expression on your right-hand side is also growing. So they will balance out, or finally it will get constant.
You will balance.
Yeah.
You will see that we will see in the next lecture that from this expression will be equivalent under a little bit more than this. As I say, this is singleton. If we put strict singleton, this condition will become equivalent to a new type of ergodic theorems that came out just from this consideration. And they were, we called them in a paper long ago with Obata and Hashimoto, we call entangled ergodic theorem. They are very different from standard. So, now there is some literature by many authors in the world who began.
This game started by Weidenfeld's long back,
not entangled ergodic theorem. But I call von Waldel's lemma because essentially the fact that it doesn't depend on positivity, that it doesn't depend on the fact that the map is a scalar valued, and that you get essentially pair partition. This and the basic combinatorial argument that unfortunately I cannot do today, but I will do tomorrow. Everything was in his paper.
Okay, so the Spiker thesis actually he exploits more.
This is a little. I mean, he had many more assumptions, yes, of course. But the basic idea was by him. That is why I call von Waldenfeld's lemma. You see, because the basic idea that only pair partitions survive. The Gaussian bound was in the paper by Obata and myself, Obata, Hashimoto and myself, and also the entangled ergodic theorem. You will see. Entangled ergodic theorem are really interesting. And you will see that they come from, canonically, from this point. I don't know, I think what I should stop now.